Good afternoon, everyone. And thank you for coming to this session where we're going to be talking about leveraging C++ 20 and 23 features for low-level interactions. My name is E Erickson. I work for Altera, an Intel company. We build FPGAs, and inside that FPGA business unit, I am part of the embedded systems team. So I work a lot in embedded software, and hence this talk. So I'm going to share with you how you can, in a bare metal environment, demonstrate effective use of C++ in the low-level interaction. And when I say low-level interaction, we're talking about hardware interactions or interactions that are bit-level manipulations. I'm going to give a little bit of my opinion, but I think other people could come to a similar conclusion about how we ended up with C as the principal language in hardware interactions, talking about how you can effectively leverage both the features of C++ and code that you may have that's already written in C, and do it in a modern fashion. And finally, really it's the second half of this talk, is how do you use C++ alone and ditch C? It's not to say C is a bad language, but C++ has some advantages we'll go through, and I hope that this talk inspires you to explore this in your projects. So why is C so prolific? It's the kernel. The reality is that 30 some odd years ago, or 40 some odd years ago, when people were writing operating systems that had to interact with hardware, it was all done in C. That was probably the best language to use at the time. It certainly was one of the better established languages at the time. And that made organizations very comfortable with C as the means of hardware interaction. And I can't tell you how many times in my career I've heard somebody say, C++ is slow, C++ is bloated, C++ is clumsy. And that leads to a bias in our industry. And part of the goal of my talk today is to hopefully undo some of that bias. What are the advantages of C++? Whoops, my mistake. What are the advantages of C++? Why would you want to do your hardware interactions and your bit manipulations in C++? Well, it gives you a few very important features that let you worry about less stuff and write more code that becomes product for your customer. It gives you lifetime management. And principally there, I'm talking about smart pointers. It gives you type safety that is more rigorous than what is allowed in C, or that C provides. That typing system is sophisticated and is a strong one. And we'll show a few examples of how C++ is superior to existing C constructs in that area. Beyond the hardware interaction, when you come above that, there are opportunities to write less code through things like inheritance and polymorphism. But you may still need to interact with kernel APIs that are still written in C. You may have existing APIs of your own of very well-proven algorithms, and changing those are not easy. And there are some cases where you may just need a raw pointer for some part of a test or part of a product requirement. So make sure that you use C++, but don't negate the advantages in C++ by creating dangerous C-like code. And we'll talk about what that means in a couple of slides. The obvious question then becomes, let's rewrite all the code in C, from C rather, into C++. Rewrite all the C code. There's lots of code out there. And it's in my references. If you pull the deck out of Discord, Strausstrup highlights this more from a what would it take to rewrite all the C++ code in the world from his talk last year. But suffice it to say, I've gone through this exercise on a much smaller scale, and there is a lot that gets in the way that makes your timeline longer. A lot of the thoughts you might have about rewriting your C code in C++ get negated very quickly when you realize how many tests you might have to change. Or if you have time critical code, you have to go revalidate that code on hardware. So use some caution around rewriting your code. I'm not trying to say make work for yourselves. I'm trying to say make your code safe, but don't undo good work that's been done in the past. If I were to choose the degenerate case of this, it would be the Linux kernel. We are not rewriting the Linux kernel all at once. We could probably do it, but it would be a Herculean effort that's likely intractable. So you've got to keep using some amount of C code. You can't throw it all away all at once. At best, you're going to go through a graded migration from C to C++. But we want to make sure that we use that C code in line with C++ best practices. So I gave this preview on the intro slide. There's lots of reasons to use C++ that enhance the safety of your code. The lifetime management, and in this case, we'll be talking mostly about unique pointer of the shared pointer options. I'm sorry, of the smart pointer options. They handle the allocation and delete for you. So you don't have to worry about matching every new to every delete the way that, say, 20 years ago we had to in C++. Strict typing. You can catch a lot of errors at compilation with C++ that you won't necessarily catch in C. And finally, standard tests, and when I say standard test, I mean the standard libraries test suite, has many useful tests that are well beyond the scope of libc's offering of, say, static assert. And I talk about a few of those tests later in this talk. So I said smart pointers are great. They are great. They handle the allocation. They handle the delete. But underneath it all, in every smart pointer, there is a reference that is a naked pointer or a raw pointer. And there's an API for that. You can use the get of the unique pointer to get the underlying raw pointer and then go use it in C land. I think it would hopefully stand to reason that you can't simply give the unique pointer object to your C code. You have to pull that raw pointer out from underneath it so that the C code actually knows what it's talking to. Otherwise, you're going to be talking to this unique pointer C++ object. Sounds great. I have a way to get the raw pointer to hand down to my existing C API. And then, of course, after you've completed the call to my C API, you can go to your next function and do it again, right? The answer is maybe. And the reason the answer is maybe is because of the nature of the get function. That getter is giving you a copy. So when you think about the use case, you're allocating something in C++, buffer object, whatever you might need to pass down into C. You then want to get the result. There's a synchronization problem. And I'm using synchronization here not in the context of thread synchronization, but in the context of synchronizing the C runtime to the C++ runtime. Your underlying C code may have changed the pointer. There are innumerable functions that will do something on a pointer and move it and then give you the moved pointer back. Or it may have deleted and reconstructed an object and given you the new pointer back. So you don't really know what's gone on behind that C firewall. So you have the synchronization problem of what if the pointer moved, and you have the memory safety problem of what if my C code deallocated and reallocated my object. Well, the standard library has some syntactic sugar for this starting in C++ 23, and that's in-out pointer and out pointer. There's a slight distinction between these two. In this talk, I'm focusing almost entirely on in-out pointer. So let's go through this example where you would create your unique object that's pointed to by a unique pointer. You're going to hand it into your API. You're then going to get the result back and hand the pointer to the next function. And here you can see this syntactic sugar does a lot for us. It gives us this very clean look. I'm going to call the API and I'm going to explicitly indicate this is a pointer that is an in-out pointer, and I give it the unique pointer. And it does some magic under the hood. And we're going to talk about what's going on there. Then I can just use it again because the syntactic sugar has reset the pointer for me. This gives you a much more clean, readable code base. It gives you a very clear indication that you're leaving the C++ world and going into the C world, or at least you're leaving smart pointer land and going into raw pointer land. So just to emphasize it again, you're going to call your API. You're going to use the pointer. You're going to call it. You're then going to use the pointer again on the next API. And this all works. The reason is, underneath the hood, any smart pointer, I keep saying this, does have a raw reference. Both of them pass that raw pointer to the C function when you call it, both in-out pointer and out pointer. When the function returns, in-out pointer is reset to whatever value came back from the C call. So it's roughly equivalent to these 5 lines of code. You've created your unique object, you get the pointer. So I have a raw T pointer reference here. You pass it to your first API. Your first API does the magic that you've designed it for. The pointer comes back, it may have changed. So the smart pointer gets reset. You put the raw pointer and update the unique pointer's reference, and then you're free to pass it to the next object. To really drive the point home, that smart pointer get function is a value. So if you change that value outside of smart pointer land, in C land, you need to come back and update your smart pointers. And to really re-emphasize it, if C does anything to your pointer, your C++ pointer will be stale. The in-out pointer and the out pointer get you the syntactic sugar to handle that update so that you no longer have a stale pointer when you come back. When we call across this boundary, the way that C represents objects and the way that C++ represent objects are quite similar. But there's some funny things the compiler can do in C++. One is it can reorder the memory layout. So in this case, I have a class. Imagine that there's more in the class than just these 3 ints, but they have different access modifiers. So you have some private, you have some public. The compiler is allowed to reorder in this case and move your integers around in memory. It probably doesn't, but it's allowed to. It's important, though, to make sure that your objects can be successfully handed to C and come back. This is but one example of how the C++ side of the problem can complicate your situation. There are a handful of rules. One is you have to use the same access modifiers, same access control. You want no virtual in the object that you're passing in or any base class, so be careful about abstract base classes. Your non-static data, you cannot have non-static data members in the most derived class, and all the base classes must be standard layout. And all members of that object need to follow the rules as well. I'm giving you a super high level 50,000 foot glancing blow at that. If you take a look down here, I reference Andreas Fertig, who's speaking across the hall, and he has a much more detailed write-up of everything you have to do to successfully cross the C++ boundary. Understand that there are rules. If you follow the rules, this will work. If you go to a good reference and understand the rules, you'll design a good object. But like all good software engineers, we don't trust our code. We want to test it. Standard library will do this for us. And the 2 things you need to satisfy for the C++ memory compatibility are your type needs to be trivial, so it supports standard static initialization, and it needs to be standard layout class. Again, I'll refer you to Andreas Fertig's details on how exactly you make a standard layout class, but I can say that one solution to this problem is a struct, and we're going to use that in a second. So we've gone through how do we get from C++ to C in a way that the data is represented correctly on both sides, in a way that we capture side effects in the C call so that we don't have stale pointers in the C++ calls. I'm now going to try to take you a step further and talk to you about breaking free of the kernel. We use C because kernels use C. And when I say kernel here, I'm not really referring strictly to the Linux kernel. If you look at other real-time operating system kernels like real-time operating systems, they're almost exclusively written in C. So therefore, if you're writing some bare metal code, you're writing your own way of interacting with the hardware, you're writing your own operating system, just do what the kernel does, of course. I challenge you to change your thinking. Don't just do what everybody else has done. That is not something that grows our industry or our discipline, and it will not make for better code in the future. I've already mentioned C++ has advantages, so take advantage of this language that has been created for us, that we are all part of, that we use, that some of us maintain. So If we talk about hardware access, there are very simple, naive ways to access hardware from C++-like constructs. And here's a really obvious one. We have a class. The class is UART. One of the more common things that you need to do in a UART is set the baud rate. So I could have defined somewhere this address. Where's my baud rate register? And I could have a function that sets the baud rate. I could have a function that gets the baud rate. This will work. But you'll notice there's a couple of not so best practices going on here. The first one is we're using some raw pointers in here. This baud rate reg is a constant somewhere that's been set equal to the base address of the UART or something to that effect, or to the offset inside the UART IP. And we're just raw dereferencing it. It'll work, probably not the best choice. The second thing is we're creating a lot of functions. There's a get and a set for every register if we go with this path. Gets and sets per register, again, work, but they create a lot more, I contend, they create a lot more effort in test. Number one, you have more APIs to test. Number two, that is more difficult to mock if you wanted to mock the underlying hardware interaction, because you have no easy way to substitute your mock object here when the rate gets written to it. In broader object-oriented programming, there's an idiom called PIMPLE, the pointer to implementation idiom. This is done to avoid having to recompile the calling code if your underlying implementation changes. So we're doing a good encapsulation here. We're saying that our implementation is entirely contained in another object that is pointed to, and we don't see it in the declaration of the class in the header file. This helps, and there's a reason that general C++ uses it. So we're going to take some inspiration from this. And we're going to talk about what I call PIMPLE-inspired register access. So don't do a pointer to the implementation. Instead, do a pointer to the register set. I mentioned earlier that one of the constructs that will satisfy both trivial type and standard layout is a struct. So I've created a struct of registers here. And I'm only showing one because I only showed you the baud rate register in the last example. I can then point to those registers inside the UART class, and then my member functions would all be referring into this object that is pointed to get to the hardware. A couple of key distinctions here. I now have a container, the struct, that I could pass to a C API and get good hardware access out of if I needed it. The second is, this is a more testable piece of code. Why is it more testable? Well, if we do a good bit of dependency injection here and make your constructor take a pointer to the registers, now you can say at runtime on the hardware, I put the base address of the hardware into this constructor and everything runs on the hardware as designed. If I'm in testing, I can allocate up a mock object that conforms to that structure, or in the case that that is a class, you could inherit from that class and you could make a mock object easily substitutable into your class through dependency injection. So any object that can be casted from the UART regs or inherited from that can be handed into the class and you get an easier test harness. Last year, I talked about a concept called a hookable register. I'd invite you to go look at my YouTube video about that, but you can basically overload the concept of uint32 with a type def, and you can substitute your uint32 with a uint32-like object that gives you read and write hooks. I'm not the first person to propose that, but that lets you inject side effects into your tests. When it comes to the definition of this register set, I'm saying it's a struct, but it needs a couple of attributes. And I've kind of broken this out in the old style of attribute, so I apologize for folks who are wedded to the modern C++ attribute syntax. You have to both pack it and potentially align it. The packing is important because we're doing regular 32-bit access. I'm assuming that our registers are 32 bits wide. And if we were on a wider system, we want to make sure that the compiler doesn't leave gaps for us. So the packing is important to make sure that when you look at this and think this is a set of offsets in memory, that's actually the way the compiler represents it when it builds your code. In some cases, if you're on systems that require aligned access, explicitly saying that this struct will be aligned at the alignment of your system will allow the compiler to take some shortcuts where it can avoid byte operations. It can also avoid crashes in the event that your compiler isn't savvy enough to properly do the word writes. So you're basically cueing the compiler with the alignment to say, you're allowed to do some optimizations on this with the assumption that the base address is aligned on a 4-byte boundary. And then you print out your, or you define your registers, and you include any padding regions. So I just highlight this here because oftentimes there's gaps in register sets due to the way that the underlying hardware has been configured, where certain registers won't apply in the parameterizations that your hardware counterparts have chosen. And you have to make sure that you account for the pad regions. This is also something that is inherently scriptable. There are design collateral that are used by hardware engineers that are XMLs. The principal standard is called IP-exact. And you can parse out IP-exact to generate register sets, where you essentially say, here's my XML, my memory space, go through some parsing, generate structs. And then you're able to say, my hardware and my software match. To the point where if you really wanted to, you could hash that IP-exact file and build that into your code and say, if this IP-exact has this hash and this code has that hash built into it, these two pieces should work together. Final point on this, you'll notice that every single one of these registers is volatile. That's incredibly important for hardware access because you have no idea what hardware side effects are going to occur. Particularly in the case of, I don't know, say an interrupt. The reason for the interrupt is that some state in the hardware has changed asynchronously from your code. That asynchronous change needs to be captured, and you need to not let the compiler take any optimizations on the assumption of the value of your registers. Volatile achieves that. It's telling the compiler this can change without you knowing about it, so don't go optimizing and accidentally miss a read, which causes you to fail to acknowledge a side effect from your hardware. So we were talking about how there's this smart pointer to this register set. And I kind of broke this out to go through it step by step and then show you what I think is a more syntactically cleaner way to demonstrate what these 3 lines of code do. Somewhere there's the base address of this register, the register set. That number is going to come out of the IP-exact. I just spelled it out here as some hex value. You're probably going to parse that. You're probably going to parse that and put it in a header file and use it. So that if your incoming hardware definitions change, your software definitions automatically update. You then have to take that integer and you have to make it a raw pointer. And to do that, you got to bring out the big hammer and tell the compiler, reinterpret cast this thing from this number into this raw pointer. The reason you're doing this is you didn't allocate this. This is defined by a piece of collateral outside of your code. So you bring out the big hammer, cast your number, and say that's where the registers are. That's what those first 2 lines are getting ready to do. Finally, in a previously declared unique pointer, you reset it and say, point to the address that I told you to point at. 3 lines of code does a pretty good job. Rather straightforward. Now you can point at your register set. And you can condense it to 1 line of code, where you just reset and put the reinterpret cast inside it. You could also do this at construction. So just in your own head, drop that reset and put that constructor up against the pregs. Off you go.
Can we create like unique? Can we use also like unique in this case?
Can you use make unique? I believe the answer would be no, because make unique is going to call the allocator. Okay. And we don't want an allocator anywhere in memory. We want the allocator at this address, or we want this register at this address.
In order to use make unique, you have to provide to make unique the custom allocator for that.
You could also do this with a custom allocator, yes. And we're about to get to custom deleter. So when you leave scope, you're going to crash. And that's because the deleter is going to crash it. So when make unique runs, to the point in the question, it's going to grab a piece off the heap. It's going to allocate up that space. It's going to point the unique pointer at it. And then after you leave scope, the reference counting inside the smart pointer is going to say, I'm done, free it. Well, if I free on this address, it doesn't know what that address is. And you're going to end up in an exception at best, if not a hard crash. There's a way around this. When we think about smart pointers, you typically think of them being declared something like this, where, okay, there's a bunch of magic inside these three dots. I'll confess I'm really minimizing the elegance. But you think of it as it's templated to some type named T. And therefore you can point at anything. But in reality, there's two elements to the template. And one is the type name, and the second is the deleter, which is by default delete. Default delete is what's going to go under the hood and free that object for you, which is the reason you want to use the smart pointer. So you can write a custom deleter, and I'm highlighting here that shared pointer and unique pointer are different. And I am not advocating for you to use shared pointers in hardware access. I hope we can appreciate that multiple ownership creates some problems here, and you don't want to use the shared pointer. This is mostly to highlight the middle part of the slide, which is right here. The unique pointer's deleter defines a new type. The shared pointer's deleter is passed into its constructor. This goes to the point about C++ type safety. I can't hand a unique pointer that has a different type of deleter into a function that is expecting the default deleter. I can also, or I could actually hand the shared pointer in that case. So it's an example of C++ type safety that is to your advantage because you're ensuring that your deleter matches your implementation. Here I give an example of a really dangerous custom deleter. This is a really dangerous one because it's templated against anything. So any T could be there. We could call that a type name T, and it'll just do nothing, which completely negates the purpose of unique pointer. It's not freeing the object for you. So don't template it. Understand the deleter needs to exist. It needs to overload operator paren that takes a T star, and then do nothing in this case because we don't want to delete our hardware. So now what do meaningful functions look like? We've established how this unique pointer has to look. What do these meaningful functions become? Well, let's put the past few slides together and we come to something along these lines. I have a unique pointer. It points to my UART regs. It has a no deleter that is specific to this IP. This is actually a huge advantage because if there's some amount of cleanup you have to do in the IP block after you stop using it, here's your chance to do it. The deleter can help you clean up your IP blocks.
Kind of finalizer like in other language, so the deleter clean up the garbage.
Let me keep going and take your question at the end. I appreciate what you're saying. Let me get through the slides. And you'll note that this now uses that and reads into the baud rate register that is inside this struct that's on the other side of the pointer. So now, apologize for that running off the bottom, but you've already seen the custom deleter. So what do? You do three things to do pointer to register hardware access in pure C++. You create your volatile, packed, aligned struct that defines your register set. Then you create that smart pointer and you initialize it to the appropriate base address. And then finally, you use a type-specific custom deleter so that you don't try to deallocate the hardware. We've gotten to the registers. We've worked our way down the call stack and we're at the hardware. How do you manage the individual register interaction? So if I back up for a second, right here I'm doing, back up again. Right here, I'm doing really basic just set and get. But if your function is something more sophisticated, you don't need to set and get the whole register, you just need to set and get a bit. Or there's some pattern of bits that need to be manipulated in response to the definition of your function. How do you do that? Whoops, I'm going the wrong way. Okay. How do you do that? Something like this will work. These operators are all valid in C++. And this looks like C code. I've got a value, I'm setting it to 0. And I set a bit by ORing it with a 1. And I clear that bit by ANDing it with the opposite. Bit negated, done, clear the bit. You can do this a little more effectively in C++ with some strong typing. And I want to really emphasize the motivation for the strong typing. Additionally, constexpr can work to your advantage and move some code out of your runtime and into the compiler. I'll highlight that in a second too. I hope that a lot of you have seen something like this before in some C code. It's a really common, let's replace some bits in a register. And I also hope that everybody in the room knows, or at least can appreciate, that this is really dangerous. The reason it's really dangerous is when you do this preprocessor pound define thing, the compiler takes whatever you give to the function like macro and simply replaces, like Control F, replaces whatever X is here and sticks it here, and whatever the mask is and sticks it in these two places, and whatever the bits are and sticks it in this place. Is this particular example of a preprocessor definition going to radically break our code or create a hugely dangerous scenario? Probably not, because we have some operators in there that only work on certain types. But there are myriad examples of hash define really being very risky in C code. The reason we do this is because there's a perception that it's faster. But I'd ask you, is the moderate speed up you might get from this worth the risk? Let's compare it to how you could do this in C++. Std bit set allows us to both define the width of the operation and use a strong type. In this case, I'm saying do the replace bits on any number of bits. Just give me an n. And this should probably be limited to some extent to just be 8, 16, 32, 64. But conceptually, bit set will take any number of bits. So you define your n. I've got a nice templated function here. If I've got to replace a 16-bit register, I use n16. If I'm doing this bit replace on a 32, n's 32. Doing it on a 64, it's a 64. And in the case of the mask in particular, because the mask sometimes is based on a combination of other bit fields. So say the mask that you're clearing is defined by other bit sets. Then you can make that composite mask that is covering multiple bits in your register as a constexpr. It would happen before you got to this point. You just pass that constexpr into this function. But this function gives you a strongly typed, macro-like, constexpr-capable bit manipulation function. So let's talk through some more positives about doing bit manipulation in constexpr. First of all, this first one should be a constexpr. Go ahead and insert that on the left-hand side here. I can define a constant very easily. I can put a whole bunch of math on the right-hand side so long as it's all known at compile time. Again, I'm trying to emphasize to you, shift your work out of your runtime, put it into the compiler. There's a similar standard library feature that it can also be a constexpr, and that's bitcast. So if you've ever run into a scenario like I did several jobs back where we had to pass some floats over a network, getting the float to be an int32 to shove into a data structure to send over the network was like a struct union combination of horrible C code. In C++, you can do it with bitcast. just cast your float to a uint32, and it will take the on-memory representation of, in this case, 1.0, and give you the bits. And this is just a pet peeve of mine because I did it once and didn't understand why the compiler was failing, but I did this first line. It wasn't constexpr at the time, but this would also apply to constexpr. 0xe plus 1. Does anybody know what the compiler actually does there?
Converts into a double.
Not quite.
Converts that into a signed integer?
Not quite. It tries to make 0x 10 to the 1 power. You can look it up. It's called maximal munch. There's a bunch of examples of this. And the number 14 is lucky that you end up in this situation. So this first one isn't going to work, but then you can define, I just called it 14 as E, and then you can define 14 plus 1 and get 15. It's a trivial example to emphasize that it's a way to get around maximal munch if you ever hit some like, why is the compiler throwing this horrible error at me? I don't know what I did wrong. And then you say, wait a minute, let me break up my expression so that I can make several constexprs and put them together. It's a workaround if you're pounding your head against the wall like I did for 6 hours on this one. Okay. Oh, by the way, just to elaborate on that, this occurred for me because my +1 was in a hash define. So basically I had a hash define that was an E and a hash define that was a 1. I didn't have the parentheses in there. I then put the parentheses in there and it still tried to make a 10 to the +1. So it's one of the more memorable parts of my programming experience, as you might tell. Okay. I mentioned endianness. I gave this example of I got a float out of some math. I need to pack it into some network traffic. There's more than a few times when we have to swap some bytes, okay? Network traffic has all sorts of byte swapping in it because your network endianness and your processor endianness in the modern era generally don't match. Your network traffic's gonna be big endian and your processor traffic's gonna generally be little endian, although you might have a setting in the hardware that you can flip there. Cryptographic endianness is always big, and therefore you have a lot of reasons to want to swipe some bytes. And finally, my personal favorite, the hardware bug, because yes, this does happen. I think anybody who's worked in silicon engineering, I'm not sure how much of the audience does that, this has happened before. And I say it has happened so frequently because now the standard library has byte swap. So what does that look like? Std byte swap, and it'll just do it. It's happening so frequently that you can now look to the standard library for your implementation. When it comes to this, I say, slight typo here, it can be a constexpr. So in the event that you are just like, I've got this big number and I know it needs to be swapped, so drop it into byte swap. You can make that a constexpr, but it can also just be used to swap bytes at runtime. And then there's also swizzling. So if you do byte swap across an array, you can swizzle the array. And that's my experience with this. I had an occasion in my past where there was a definition of a stream of data and the hardware had the endianness wrong on like a word level or so, and we had to go swizzle that array. And the amount of testing that our bosses want us to write around that to make sure we didn't swizzle incorrectly was very large. And if I could just point to the standard library and say, I trust the C++ language, I think my management would have been much happier with me. I want to highlight a couple of related things that I see are coming up in C++26 based on what's currently in the pipeline there. By the way, just to be totally clear, I am not a developer of any feature that you've previously seen in this talk. I use it and I'm trying to encourage you to use it. I'm not a developer of any of these C++26 features. I expect to be a user and I'd like you to try using it. So the first thing is saturated arithmetic. So there's times when you want that register value to roll over and there's times when you don't. And I can't tell you how many times I've had to write if x plus y greater than max int, max int. This lets you get around that in a much cleaner, more syntactically friendly way. It has some use cases, definitely, if you have scenarios where you have hardware that does not expect rollover. And then minor formatting bug here, I apologize. Static reflection has all sorts of fun ideas. So if you have static reflection, you can enhance your debug code. Instead of saying enum54 failed its unit test, you can now go do reflection and say, here's the value of the enum that failed its unit test. So developer friendliness is coming in that regard. Fetching members by index, so looping over the members of a struct or the members of a class right now requires some custom code. There's some ways to do it in C++ 20 and 23 that I don't talk about here that are, I don't think, syntactically friendly enough. The reflection's the real answer. And then finally, I already mentioned one of the testability improvements, but you also have the potential to have compile time improvements. And by compile time improvements, I mean more checks at compile time, because you can use the reflection to make sure that your code's matching your documentation. Okay, I'd like to just kind of bring it all together and say, we as developers, those who use C, have to do a lot of out-of-band work to make it safer. There's static analysis. There's defined required compiler flags in most organizations. There's a whole lot of in-depth code review. There's a whole lot of testing. And generally speaking, I think personally, my opinion, that amount of out-of-band work is much larger than the in-band work, so to speak, of modifying those critical pieces of code to use language features that we can rely on. Really emphasizing that C++ has its advantages. Strong typing and a more thorough type system makes the code safer. You got the lifetime management that we talked about. C++ takes those questions of did every new have a delete, did every malloc have a free off the table. You're probably not going to ship your code without static analysis. I think most organizations expect some amount of static analysis. We're definitely going to need testing, but you can get the compiler to trap your errors earlier. So you've got your compiler being able to catch more problems sooner so that the developer does not attain levels of false confidence that are later dispelled or cause the disappointment when the static analysis checks fail. My company's doing this. I hope you do this too, because it'll make better code for everybody. I thank you very much, and now I'll take your questions. Would you mind using the microphone?
So one issue I see with register maps in particular with FPGAs is when you pack the array, often your address to the underlying type is not aligned to the type. How does Altera typically handle this? Do you just be careful when you access it, or?
Let me try to understand your question.
Yes.
Go through that one more time.
So when you pack this array, sometimes the pointer that you're going to access this register through is not aligned with respect to the alignment requirements of the type. So the uint32, the uint64, whatever it is, it's aligned on an odd word, odd byte. So the standard way to handle that is to memcopy it out whenever you do that access. But that's a very manual process, and I often see cases where somebody just dereferences the pointer or passes it into another function that does that and causes undefined behavior. Can we do that more automatically?
Okay, so not commenting on any Altera products.
Yes.
Just to be clear, because you asked me how Altera is doing that. I'm not commenting on any Altera products. That is something you need to catch very, very, very early in the design cycle. You have to help your hardware counterparts who might not be processor experts understand and appreciate the meaning of alignment on the knock. And the only really effective way to do that is to trap it at a design review and say, we're always going to do this width. It's always going to be this alignment. This has ripple effects, the alignment concern, across many things beyond simply the hardware access, because you end up with page table bloat when you have to like cover the edge of a page, or you're off by one at the end of a page because of a problem like this. So, and that causes deeper lookups, which hurts performance. Or, additionally, if you have an off by a byte error in there, If you're on a platform that requires strict alignment, you're definitely going to fail. So to put this all like into a concise answer, your problem occurs well before you ever wrote your code. It goes all the way to the hardware design of the register set. And you just have to put some rules on the hardware design.
Okay, so just to clarify, don't do that as the response.
Don't do that as the response. At the time that you define your register, say my alignment is my architecture's alignment and my size is my predefined size, and stick to it.
Hi, thank you for the talk. I just wanted to clarify this use of unique pointer here, the advantages, because you didn't mention this, but the main issue with the smart pointer, unique pointer is these are owning pointers. Mm-hmm. So what we gain from using them, they automatically delete the own objects. Mm-hmm. And here you did, actually you did the raw pointer behavior from this unique pointer, just making this deleter empty.
Right.
Thanks.
The reason for it is consistency and style across your code base. So if your developers are all looking at the code, like let's say you get into a code review with a non-hardware interaction person, they're going to be generally expecting smart pointers throughout the code. So what I'm saying here is don't break the pattern. Don't make it this unusual thing. Yeah, sure, you can use a raw pointer. You can definitely use a raw pointer. I'm saying that for the sake of people who are not interacting with the hardware, understanding the code top to bottom, keeping the implementation pattern consistent has value and might get some of those folks who are not necessarily working with the hardware to be willing to work with the hardware because they don't get scared off by this raw pointer. It's really it's a pattern implementation consistency thing. There's no real functionality that's being added there. But I would encourage you to consider implementation consistency.
Hi, thanks for the talk. One thing that I've done in the past is use the guideline support library. It has a type called not null, mm-hmm. which is a smart pointer that basically just makes sure that you never set it to null and you can never change it after it's set and it doesn't get deleted. So it would be perfect for this kind of register type stuff. I
was unaware of that. I appreciate the comment. Yep.
And it looks just like unique pointer in all of their aspects.
Okay. I appreciate the comment. Again, I'm trying to stick to the language standard itself. I'm sure that there's other ways to represent it.
You have used, thank you for the talk, and you have used a structure with attribute packed. Mm-hmm. There is one more pragma pack. You can also use that. Could you tell me or us what would be the significant difference between them? And is there any order difference, like packing of structure with, like, if I pack first my bigger uint 32, then uint 8, and then character? The packing order does matter for performance?
Take the second part first. In a well-defined register set, or well-defined struct based on a register set, firstly, I would not think we would have packed registers, packed structs to represent the registers. I could see an argument for saying I could see an argument for that if there's subsystems inside an IP block. In that case, I would have to test it. I don't have the answer off the top of my head. I would assume that if each structure were packed, no, I take it back. You shouldn't do that. You should just lay out your registers side by side. So let me go back to the IP exact example, right? So you're getting this XML from the design team, or you have some other collateral that defines the hardware. Those maps are almost always flat, meaning they start at 0 and they go to however big the memory space is. Therefore, you should keep the structure flat as well. Nesting the structs inside each other might be worthwhile in other areas, but you just end up with, like, I would call it not the easiest to read code when you're trying to do your comparisons. So I'd encourage you to not nest structures. In terms of, like, the behavior of packing in nested structures, I can't answer that as I'm standing here. Pragma versus attribute. I would want the attribute because you may have structs that you don't want to be packed. I think attribute is cleaner syntactically, personally. You know, seeing this really explicitly shows, you know, this is a common pattern in GCC or any or other compilers as well. This is explicitly saying I'm hinting to the compiler, do this pattern of things on this one thing. Pragma packed probably also works. I can't say that's my coding style.
And I have one more question regarding like if you have some, I had used some Xilinx libraries that have like non-const parameters, and if I'm making my API with const parameters, then I have to use constcast to remove the const. Like, is this like how to like improve new APIs for future generation? Should we like make all the things every const, or we should like with legacy constcast we should use like this, or how?
I'm not going to comment on any implementation that Xilinx may have made because I'm just unfamiliar with it. In general, you want to follow what I think are pretty much best practices in C++, which is when you're passing in to set, then the parameter going in is const. And when you're reading out to get, you have the trailing const. Like that. That's what I would say your get and set function should look like. How other people do it, I couldn't comment on.
Okay, thank you so much.
Thanks for the talk. I noticed you used std bit set, which is kind of new to me. I believe in C++ 17 there was a std byte type, or it was introduced somewhere, I think 17. Do you have any experience with kind of mixing or plan for how to interoperate, or do you just use std bit set 8, you know, typically?
Okay, so let me, I'm sorry, was there more to your question?
No,
I
that's
didn't catch up. Okay, so let me pop ahead to that. Okay. Std bit set's explicitly a constexpr, and there might be reasons that you would only use 24 bits if there's only 24 valid bits in the register. In terms of, you know, personal preference, where is it? Backing up. I'm a standard int type, so I'd be using uint32t for byte word, and I'd be using uint8t for std byte. I would expect those to be interoperable, but I can't say I have experience with std byte per se.
Yeah, I think some analysis tools, maybe SonarLint, if you use uint8t and then you do kind of bitwise arithmetic on it, and it's kind of, it'll say, you know, use std byte as the type. That's just my experience. I don't know if it's due to cross-compiling or what, but that's just my experience. But so you would typically use uint8?
All my code uses stdint, uint with t or int with t. Again, that might be a setting in your analysis tool. I don't use that analysis tool, and I can say that against all of the checks that we put in there, we've never had a problem with the stdints.
Thanks.
Any other questions?
Just to comment on the std byte thing, it's generally safer than in some very subtle ways than uint8 if you have a really weird standard implementation. But the problem I've always had with it is that at low optimization levels, 0, 01, it is so slow. It's unusable in my experience, just because the compiler can't elide all the necessary boilerplates.
Okay. Well, like I say, I have no experience with it, so I'm glad that you were able to give some feedback on that question.
I've been trying something similar to this, the re-implementation of the system call interface in C++. And one of the things that I've been encountering, and I was hoping to get some insight into here, was like, what do I do about all of the things that are essentially bit sets or portions of bit sets and having nice types to represent them? Are there like standard ways to go about doing that? Accepted idioms? That's, yes.
Accepted idioms is
I don't-
a stretch.
Yeah, I don't really like mentioning like actual bit values directly.
So one thing that bitset as a constexpr can do is you could define all of those bit values as the constexprs and then use them. Follow up with me separately to understand a little bit more about what you're running into there, because I think you're on the right track, so to speak. I'd want to better understand the situation that you're running into, but I would say that if you've got syscalls that are using existing standard ints, you can either represent it as standard ints or you can represent it as bit sets if it's some number that's between the standard int widths.
Mostly what it is like, oh, read, write, and all of those other flags. I want to, like, they're named because they're defined. I want to change their names, and I want to have like, make them into C++ things instead of barely, obviously translated from C.
So like const standard int flag value equals number.
Right, but then why would you OR them all together? Isn't there some data structure you can put them in, right? Like treating them just as fancy ints seems like the wrong thing to do because that's not what they are.
Yeah, no, that's a fair point. I'm not sure, off the top of my head, I don't have a better solution for you. I'd be curious to chat with you about it later.
All right.
Anything else? All right then. Thank you all for your time. I really appreciate you coming. If you have follow-ups for me after we're done here, I'll be hanging around for a little bit.